Now we're going to look at the angle, or the angle conditions. And this is where we really kind of part the ways when we for Euclidean and hyperbolic geometry. If you notice, so far, the side angle side postulate is actually valid in Euclidean, spherical, and hyperbolic geometry. The angle side angle theorem and the side theorem are valid in all three of those geometries as well. The angle side condition is enough to make congruent triangles in hyperbolic and Euclidean, and it is enough to make it in spherical geometry if the sides of the triangle are less than pi over 2, but not in general for spherical geometry. But when we get to angles, then then things are significantly different in Euclidean versus the other two geometries. So let's take a look at that. So something interesting happens here. So in Euclidean geometry, we can have an angle here and an angle here. Now, because of the Euclidean, we can have those two angles, but we can actually move this around here, and there are many possibilities for that other angle. Okay? Not for the other angle, but for the lengths of the sides. But in Euclidean geometry, there's not a different possibility for the other angle. So we could have more than one triangle here, and they have all the angles congruent, but they're definitely not congruent triangles. So in Euclidean geometry, the angle condition is not enough to get congruent triangles. Okay, so there is no angle congruence theorem for Euclidean geometry, or for unified geometry, because of this Euclidean possibility here. Now, however, we do have something kind of interesting, and that is, let's take a look at these distance measurements. Clearly, the blue measurements aren't equal, the greens aren't equal, and the reds aren't equal. But it's interesting if we do the ratio of corresponding ones, blue over blue, green over green, red over red, corresponding sides, making sure in this case that the ones from triangle 1 here are on top, we get the same number each time, which is kind of interesting here. So as I have it right now, every length in the big triangle here, triangle 1, is exactly twice the length of the corresponding length in the triangle 2. Okay, so we have a what's called a dilation or size transformation going on here, and we have what we call similar triangles. And we're going to define a triangle to be two triangles to be similar if and only if all the corresponding angles are congruent, but then the sides are proportional. And of course, by proportional I mean that when we do the ratio of corresponding sides, we get this same number. That's our size factor of our size transformation, or it's our proportionality constant. Okay, let's look at that on this this other sketch here. So again, we have two triangles here. Well, I have two parts here. One where I can control by sliders. So this is extremely similar to what we just saw there. And then this one, though, we can actually put in numbers. So if I put in 40 degrees and 80 degrees, now since this is Euclidean geometry, the angle sum is 180 degrees, so that forces the other one to be 60 degrees. Again, this is dynamic, so I can change this if I want. For example, if I want to make that 30 degrees, there we go. So 30 degrees, 80 degrees, and 70 degrees. So we have these two triangles, and we can measure them. Now, these yellow points can control the sizes of the triangles here. And notice, of course, there are infinitely many sizes that we can have. So again, we can't pin it down to one particular size of triangle just with the angles. We have no control over really the lengths of the sides. Okay, so here's this, let's see, there are the side lengths, here are the ratios, but there are some other ratios that are kind of interesting as well. if we do A over B1, A2 over B2, we do ratios, some other ratios that are, and this is interesting. Notice that even though these ratios are all the same as each other, the number that you get is changing. So like right now, triangle 2 is 1.55 times as big as triangle 1. Of course, there's some place in here where that ratio is 1, and in fact, those triangles are congruent. There they are. Well, they were there for the second. Okay, so now those triangles are congruent, or nearly got them congruent. Okay, now if that factor is less than 1, then the second triangle is smaller than the first. If it's bigger than 1, the second triangle is bigger than the first one. But notice these ratios over here did not change when I changed the size of either triangle. And what these are doing is they're the ratio of side to side within the triangle, and they're the same from both triangles. So that's kind of another way you can look at this. These three numbers here are not the same as each other, but they're the same from triangle to triangle. And it's really this last fact that's going to give us, make it able for us to define trigonometric ratios, sine, cosine, and tangent, and use those to develop trigonometry. So this triangle similarity theorem is really the basis of all of Euclidean trigonometry. Now, if we have trigonometry, can we solve these triangles? Well, there's no way we're going to be able to solve it in the sense of narrowing it down to one specific thing, because as you see, there are infinitely many congruence classes of triangles with these two angles or these three angles as measurements. But what I can do is I can solve them. Since they're similar, I can do a sort of a basic example here where C is 1. Okay, and I can take this triangle and solve it. Okay, so I can first of all, given the two angles, find the other angle by the angle sum theorem. That's pretty easy. Then I can use law of sines to compute these different sides for A and B if I let side C be 1. So now we're basically in the all three angles in one side condition where that is enough to narrow it down to one single triangle. We can find side A and side B under those conditions and find the area under those conditions. Now then, any triangle is then just a size transformation of this particular one by some factor, well, whatever C is over here. Okay, so C is just 1 times C, or C. The angles are the same, they don't change. But what happens is A is C times this A, the A from this guy over here, and the B is the C times this B, the B from this little triangle here. C is C. So now we have a set of equations that define the triangle measurement, and so we can get this. But notice there's a different one for every positive number C. We get a different congruence class, but we've solved for all the classes. And to finish our solving, we need to find the area, and it turns out, of course, that the area is C squared times the area of this basic triangle. So we take the area that we found for that basic one, multiply by C squared, and that gives you the area of this triangle with these measurements here. But notice that the C is a variable length. So okay, so I have this for right now. The little one, for all of these, comparing the green one to the original one there. Let's make everything twice as big. Okay, see if I can adjust it. I'll get it close to twice as big anyway. There we go. So right at the moment, all the lengths in the green triangle are twice as big as the lengths in this little black triangle over here. And the area, well, it's supposed to be 4 times as big. It says 3.99, so I'm not exactly on twice as big there. And the area is 4 times the area of the basic triangle. So we have the area of this one here. Okay, and so you can see what's going on there for similar triangles. Okay, that's going to give rise to how we define the basic trig ratios. In fact, let me just go ahead and do this really fast. So just introduce this. So if we want to, how we define sine, cosine, and tangent of an acute angle, at least for a right, we can take draw a ray, rotate it around a certain degree, certain measurement. I've done that in degrees. You could do it in radians for an acute angle. Pick any point we want on there and complete a right, draw a perpendicular from that point and see where it crosses the other side, and we have this triangle. Now it doesn't matter where we go on this triangle, then we can look at the measures, okay? But I can also now define some trig ratios. For example, I can define tangent then to be the ratio of the opposite side here over the adjacent side, and notice that no matter where I put this, it comes out to be the same thing. So that's a constant for this particular angle. Of course, it is a function of the angle, because if I change the angle, now this turns out to be a different ratio. Okay, and in a similar manner, I can define sine to be the length of the opposite side over the hypotenuse, and cosine to be the length of the opposite side of the adjacent side over the hypotenuse. So we can define all of these trig ratios, and they turn out to be well defined there for acute angles. And then of course you guys know from looking at this before from your classes, you know how to take this concept and extend the trig functions to infinitely many different things by doing them in terms of circular trig functions, which is defined here. So all this stuff is laid out in this trigonometry sketch, and you can use that to review any of these basic concepts if you'd like. Now let's look at what happens in hyperbolic geometry. The first thing is to notice is if we just do two angles that here's another one with the same two angles, but the let's see, show the distance measurements and then show the ratios just like we did on the other one. And notice that these three numbers right here, 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 and here, notice these are not the same number. Okay, and as I move this around, they all change. Not only do they all change, they don't stay the same anymore. They never were the same. None of them are the same here. And so here we have this, and the other angle may actually be different as well. Okay, so there's the other angle down there. No, I'm sorry, that's the same angles there. We could measure the other angles as well, but we do not get proportional sides here with just two angles. Okay, so let me measure that other angle as well. Let's see, measure angle. I want to go down here. Hyperbolic, half-plane tools. I want to measure the angle, and I want to measure it. Which one do we not have? The blue one. C. And then this C. And so notice those are not. Let me hide those. So those angles there are not the same. So we have so neither part of the condition is satisfied in the sense that for similarity, because similarity you have to have all three angles the same measure, congruent angles, all corresponding angles pairs, all three pairs congruent, and then you also have to have the sides proportional. And notice we don't have the sides proportional, and we don't have corresponding angles for just narrowing down two angles. So if we have some hyperbolic trigonometry, it's definitely going to work a very different way. Now, what if you have all three angles the same? Let's investigate that. Now, remember, in the Euclidean condition, two angles is matching up. The angle-angle condition was enough to give us the angle-angle-angle condition, right? The third angle you got to be congruent automatically. Now, let's see what we have here. Here we have a triangle down here. This can be any triangle we want. And let's look at what happens over on this triangle here. Okay, so let's see if we can kind of make sense of what's going on. So we want point D to correspond to point A, B correspond to E, and F and C correspond. So we start with any point D we want. We make this angle here, so we generate these two rays here so that the angle is the same as the green angle here. And notice as I change this, just look, that green angle is going to change, and it's going to be congruent. Let's see, let's throw some measurements in here. Just make this fit my screen just a little bit better. Okay, so here we have this, and we've fixed this measure of this angle here, and let me measure some angles as well. Has he already got those measured and showing up? I don't see them showing up anywhere. Okay, so let me go ahead and show some angle measures. Okay. Measure. So we're going to measure BAC, ABC, and BCA, and these I'm going to hide, and I'm going to so there we have links. Here we're going to have angles A, B, and C. Oh, that last one is excuse me, that last one didn't measure like I wanted it to. I got to put a point on here I didn't mean to have. Okay, so let's measure that again. Angle C, so it would be B, C, A. Okay. So hide that, bring this down. Let's get the colors to match. Angle C is blue, labeled in blue. Angle B is labeled in red, and angle A is labeled in green. Okay, so now just to convince you, let's measure the angles over here. So angle D should be, okay, let's do it in the same order. BAC, this should be EDF. Okay. Well, let's do the other EDF. EDF. Okay. And that's the green angle. And notice that's the same. Okay, and then we want ABC. So ABC should correspond to DFE, DF, and the E question mark down here. No, DEF, excuse me. Wrong. Yeah, that one. Yeah, we'll get to that in a minute. Okay, so this one at, let's see, at E corresponds to B. So this is ABC. So D, E, F. That angle is the same. And this one is going to be, we're going to make that red. And then finally, we're going to measure this one up here. And this is going to be, let's see, BCA. So this is going to be E question mark FD. And we're going to make sure that that one is the same as that one. That's in blue. Okay, so we get the corresponding angles to match up, and you see that as I move this around, those measures are staying the same. Now here's the trick though. We know that this point is somewhere along this blue ray, and we know it intersects here at point F. On the other hand, F is somewhere on this ray, it intersects down here at E, and we've got to do it in such a way that we get this angle and this angle to match up like they're written. But we also have to get these points. The F and the F question mark have to line up, and the E and the E question mark line up. So first of all, is it even possible to do that? And then if it is possible, how many places will it happen? And if you look, okay, there for a second we could get the F to line up, but then the E didn't quite line up. Okay, that's no good. Here's the... Okay, can we get this to work? And and what you start to find out, if you mess with this very much, it's difficult to get this thing to work out. And if we know where along here is going to make F line up and then make E line up with F where I have it. So where are we going to get this to work out? Well, it turns out there's only really one place that it's going to happen. And the circles there can kind of help us see it, because it's when that circle is set to the same radius as that red line segment, and that circle is set to the same radius as the blue line segment. And you see that the only place that we can get it to happen is when in fact these are actually congruent triangles. So it's so there's no such thing really as a similar triangle in well, I'm not sure if we saw it completely in the last one, but in this one we see that the only way that we can get the two triangles to be have all the angles the same is to in fact to have all the sides the same. When I say be the same, I mean corresponding pairs being congruent. And so this is, you actually have an angle, angle, angle congruency theorem in place of the angle, angle similarity theorem that you have in Euclidean geometry. You have an angle, angle, angle congruency theorem in hyperbolic geometry. So hyperbolic geometry has all the same congruence theorems that Euclidean geometry has, plus one more. It has an angle, angle, angle condition, but it does not have, there are no such things as similar triangles other than being congruent triangles in hyperbolic geometry. So, I should probably say this. We see that there is no such thing. Okay? And so we get this to work out. Okay? Very interesting. It turns out that in the spherical geometry as well, it turns out that locking down the three angles is enough to guarantee congruence of triangles as well. So we may come back and prove this later for these, or we may not. I'll think about that a little bit later. But we have some interesting, very interesting results going on there.